Hi! The James Webb Space Telescope has recently added another feather to its hat by uncovering the first ever population of brown dwarfs, aka failed stars in another galaxy. So in this video, let's talk about the conditions required for star formation and how, if they are not met, brown dwarfs come into existence. Let's begin. As the Webb looked closer into a star-forming region called NGC 602 in the Small Magellanic Cloud, a dwarf satellite of the Milky Way, it found not one, two, or three, but an entire group of objects called the brown dwarfs. This is incredible because although astronomers know of around 3,000 brown dwarfs in our own galaxy, this is the first time they have been discovered outside the Milky Way. Brown dwarfs have characteristics between stars and planets. They can be 13 to 75 times as massive as Jupiter and have an atmosphere just like planets. But unlike planets, they have little thermonuclear reactions taking place in their core, although these are inefficient at producing much energy like in other stars and therefore die out quickly. As a result, the power of brown dwarfs is not correlated with their luminosity, and instead of lighting up, they shrink and fade away. This is why they are often called as failed stars. This fact makes it even more incredible that such tiny low luminosity objects have been discovered by the Webb telescope at an enormous distance of around 62 kiloparsec, that is around 199,000 light years away. But to understand why brown dwarfs fail to become stars, we'll have to understand the conditions which are necessary to create them. In an earlier video, we discussed about the interstellar medium and concluded that all stars form out of giant molecular clouds of gas mostly composed of hydrogen. But despite advancements in theory and technology, our understanding of the early stages of the evolution of a star is far from complete. This is especially true for the formation of pre-nuclear burning phase objects formed out of a collapsing cloud of gas. Such an object is known as a protostar. While we do have a broad understanding of the sites of star formation, it is not obvious what conditions must be met by a cloud before it can form stars. This problem was first investigated by Sir James Jeans at the turn of the 20th century. He considered the effects of deviation from hydrostatic equilibrium and further simplified the problem by neglecting the effects of rotation, turbulence, magnetic fields, etc. The Jeans theory is based on Newtonian gravity and, as you'll see shortly, is based on the fundamental ideas of virial theorem that we discussed in an earlier video, the link to which is provided in the description below. Recall that the gravitational potential energy of a uniform spherical cloud is minus 3 by 5 gm squared by r, while its internal kinetic energy can be given as 3 by 2 nkt, where the total number of particles n can be obtained by dividing the total mass of the cloud by the average mass of its constituent particles. Then, in accordance with the virial theorem, the cloud remains bound only if its gravitational potential energy exceeds its kinetic energy, which is synonymous to the forces trying to rip the cloud apart. This condition is known as the Jeans criteria and implies that the size of the smallest cloud which will collapse is given by the corresponding Jeans length. Don't be put off by the complicated looking expression. If you look carefully, besides the constant terms, this Jeans length is only dependent on three parameters: the temperature of the cloud T, the density of the cloud ρ, and the average mass of its constituent particles denoted by a small m. Using this, we can find that the minimum mass of the cloud for a given ρ, T, and m is given by this expression called the Jeans mass. In other words, a cloud with these parameters will collapse only if its mass exceeds the Jeans mass described here. But remember that in order to derive this expression, we have neglected several important factors such as the rotation of cloud, magnetic fields, and even the external pressure exerted by the interstellar medium on the cloud, all of which may play a crucial role in reality. But how long does it take for a cloud to collapse? Let's estimate that timescale using a back-of-the-envelope calculation. Consider a particle at distance r from the center of a collapsing cloud. This particle will accelerate towards the center under the influence of the collapsing mass with acceleration a given by 4 pi by 3 g r rho. This leads us to the conclusion that if the acceleration of the particle remains constant, the free fall time reduces to inverse of square root of g rho. That is, if the initial density of the cloud is uniform, the free fall time is independent of its size, and all parts of the cloud will take the same amount of time to collapse. This behavior is known as homologous collapse. But if the cloud is centrally concentrated to start with, the free fall time at its core will be less than the outer regions, as a result of which star formation will be initiated at the center. This is called inside-out collapse. Now, this derivation may have given you the impression that as long as the Jeans mass criteria is satisfied for a large gas cloud, it will form stars of any mass, maybe even as massive as the initial mass of the cloud itself. But observations do not support that idea, because the most massive stars are at most about 100 times as massive as the Sun. That is, several orders of magnitude less massive than a typical gas cloud. Moreover, we know that stars tend to form in groups of hundreds to thousands of members. Remember we discussed star clusters in an earlier video? But that said, fragmentation of a star-forming gas cloud is expected by considering the Jeans mass equation once again. Notice that as the cloud collapses, its density will increase rapidly even though the temperature remains roughly constant. As a result, the Jeans mass will decrease. This implies that any initial inhomogeneities in the density of the cloud will cause individual regions to collapse as separate entities as soon as they satisfy the Jeans criteria. But unfortunately, calculations show that this simplified approach may create way too many stars. But in reality, only about 1% of the mass of the cloud end up in stars. That is because, remember, we assume that the cloud is collapsing isothermally and density is the only term that is changing in the Jeans mass equation. But since stars have much higher temperature than a typical cloud, it means that even if some of the energy produced during the collapse is retained instead of being radiated away, the consequent collapse will be neither fully isothermal nor adiabatic. In fact, the real situation is likely to be somewhere in between these two extreme scenarios. Once the collapse begins and the formation of stars initiates, the earliest objects formed are called protostars. Since they are unable to radiate out much energy and are embedded deep within a thick cloud of gas and dust, they can only be observed at long infrared and millimeter wavelengths. Search for such protostars are underway in many candidate sites such as the Bok globule B335 and many objects in the Orion Nebula. As this quasi-stellar object continues to evolve, its gravitational potential energy is released as heat and light and becomes the source of star's luminosity. But note that the evolution of this protostar is defined by the Kelvin-Helmholtz timescale, which is much longer than the free-fall timescale of the collapse of the cloud. As a consequence, the protostar evolution occurs at a relatively slower pace. For instance, it can take up to 40 million years for a solar mass star contracting quasi-statically to reach its main sequence structure. As the temperature of the protostar continues to increase, eventually a radiative core will develop at its center, which will be capable of supporting the gravitational collapse of the protostar via nuclear fusion. And as a result of this, the protostar will turn into a main sequence star. But this is not the case for brown dwarfs. Below a mass of 0.072 solar masses, some nuclear burning may occur, but it is far inefficient in supporting the collapse of the protostar. The objects having masses between 0.013 and 0.072 solar masses are known as brown dwarfs and have spectral types L and T. Gliese 229b was the first brown dwarf discovered in the year 1995, and since then thousands more have been found in the Milky Way itself. As expected, they are very low luminosity objects and hence difficult to observe. That is why it is incredible indeed that an entire population of brown dwarfs have been discovered outside our own galaxy. Do let me know if you found this video insightful and what else would you like to learn on this channel. Please do share our videos with friends and family. I'll see you next week. Until then, take care.